Robert Wells defined cobordism groups of immersions and calculated many examples. In particular, he showed that the cobordism group of immersions of surfaces in 3-space was isomorphic to the integers mod 8. The group is generated by an immersion of the projective plane P2. Boy's surface is an immersion of the projective plane in 3-space, so 8 copies of Boy's surface must be immersion cobordant to 0. This addition and cancellation are illustrated here. The projective plane is a Möbius strip and a disk joined along their boundary. So Boy's surface is an immersed Möbius strip and an immersed disk, the immersions matching on boundaries. Begin by deforming the immersion of the Möbius strip so that the boundary circle lies in one horizontal plane. Here's the usual Möbius strip. We deform it by stretching the lower level, making both levels concave, and raising the edge of the lower level so that it intersects the upper. The boundary circle is now a self-intersecting planar curve. Next, we immerse a disk so as to get the same boundary curve. The red circles start at the center and grow to the boundary of the disk. As they sweep out the disk, the sketch on the right shows where the corresponding points appear in 3-space. Now join the two immersions. The result is Boy's surface, an immersion of the projective plane in R3. Now take 2 copies of Boy's surface. Rotate the right-hand one 180 degrees. And join them by an immersion cobordism. This is now an immersed Klein bottle. The standard immersion of the Klein bottle is immersion cobordant to 0 because this cycle has a neighborhood which is a trivially immersed cylinder. So the cycle may be removed by immersion surgery. The cycle now disappears. What we have is an immersed sphere. Any immersed sphere is regularly homotopic to an immersion which bounds a 3-ball. The immersion now bounds a 3-ball. Immersion surgery reduces a bounding immersion to the empty set. In our immersion, that cycle appears thus. It's being traced out by this red curve. The cylindrical neighborhood is immersed with one complete twist. Here we are shortening the neighborhood, contracting it, and now we're going to expand it so as to compare it with the standard cylinder. They're not regularly homotopic. Consequently, immersion surgery on this cycle is impossible. Four copies of Boy's surface are immersion cobordant to 2 copies of the twisted Klein bottle. We tilt them slightly and join them by an immersion cobordism. We now continue the deformation by a regular homotopy. The central part of the immersion is now a product. Join 2 standard Klein bottles by immersion surgery. Then surgery on this cycle gives an immersed torus. The cycle is disappearing. Now we have an immersed torus. This torus is regularly homotopic to an embedding. The torus now bounds its interior and is consequently immersion-cobordant to 0. Here is that cycle in our immersion. It has a cylindrical neighborhood immersed with no twists. Here is the neighborhood. We straighten it out to show that it is in fact regularly homotopic to a standard cylinder. Immersion surgery on a cycle with an untwisted cylindrical neighborhood may be summarized by delete cylinder, insert disks. In our immersion, surgery will delete this cylinder and insert 2 disks, one above, one below. First, we delete the cylinder. We take it out piece by piece. Next, we insert the disks, first one, and now the other. This is now an immersed torus. The red curve is checking the self-intersection locus. We simplify it by a regular homotopy. The central portions are cut away for easier seeing. We reassemble the surface now. This is the most twisted of the 4 regular homotopy classes of immersions of the torus. Both of these generating cycles have twisted cylindrical neighborhoods. They both have one complete twist. Consequently, this immersion may not be simplified by immersion-cobordism. 8 copies of Boy's surface are immersion-cobordant to 2 copies of the twisted torus. We reverse the twist on the right-hand copy by a regular homotopy. The central portion of each leg has been cut away for a better view. Now we join the 2 by an immersion-cobordism. This is now an immersed surface of genus 2. We continue the deformation with a regular homotopy which performs a surgery on the self-intersection locus. The self-intersection locus is now connected. The central cycle has an untwisted neighborhood and may be removed by immersion surgery. We delete the cylinder. We insert the disks. We now have an immersed torus. We straighten this torus out and shrink it a bit. The cycle that goes around the center has an untwisted neighborhood and may be removed by immersion surgery. That cycle is gone. We now have an immersed sphere. The sphere is regularly homotopic to an embedding. The sphere now bounds a ball. Immersion surgery takes it to 0.